Right. So, morning. My name is Khalil. I'm principal expert for mobile systems architecture. In that role, I have duality. So I'm an engineer. I talk to people about what do the mobility solutions of the future look like and what are the technical challenges there, and we try to tackle those. But since the new mobility solutions are also a bit of a paradigm shift for us as an industry, and for our business models and for how we're used to also doing engineering. This also means that I have a bit of a chief methodologist role. So in my principal expert role, I'm also the expert on systems engineering and system of systems engineering at Continental. You can see that I believe in the adage that a good engineer is a lazy person. So you will see I have apparently recycled some slides. I promise you the recycling is very limited. But this just essentially shows that we are continuing on the same topics, basically, that noted was about last October in Montreal. Okay, so this will next back. No. Oh, there we go. Okay. Right. So I have to tell you these things, otherwise our HR and marketing people will kill me. So Continental, you might wonder, why is this guy here? If you've ever heard about our company, you probably only bring it in connection with tires. No, I don't work for the tires sector. We also are basically a component supplier. According to the business model, we're a tier 1 supplier, so we provide lead system solutions to car manufacturers like BMW, Rolls-Royce, etc. And this really does cover everything. So we build radars, we build laser scanners, we build cameras, we build brake systems, steering. We're actually phasing out of that. But we essentially build everything, and I always joke half-heartedly that we could build a car if we wanted to, but we don't. And then, of course, we have the very successful tire business. Right. Size-wise, we're about 200,000 people. Okay, so we've actually crossed the 200,000 mark again. Used to have also a powertrain division, which we've spun off now successfully. We had actually scratched the 250,000 people mark, and then we basically lost about 50,000 of those to that carve out. But we are facing the same challenges that a lot of other industries are facing. So digitalization is a thing. Please understand we are an industry of Greece and so on. So most of the people that I work with have a mechanical engineering background. Most of the people in charge have a mechanical engineering background and do have a bit of a, let's say, a default position that can be compared to Ludditism when it comes to more modern technologies. Sustainability is an issue, and I'm not only talking about greenwashing. I'm also not talking about the cyclic material economy. That's also a good thing. But I really am talking also about extending platform service life and things like that. Okay, so those are also things that are bothering us. Technology shifts is obviously something competitive environment. We're seeing whatever the opposite of globalization now is, with deeper local and regional regulations happening. So those are also things that bother us and also are important for the engineer doing, especially the system engineer. And speed is an issue. So, you know, I can develop an app in a day and a half. Why can't you do the same thing? So that's an expectation that is there. Other people are doing it for better or worse. And this is also increasing the pressure on. Again, some numbers. So again, you see automotive is essentially half of the business. Sales last year of 40 billion, projected about 44 this year. And that's me. I've spoken about myself. We can move on. Okay, and what I would like to talk to you about today is I'm not really going to go. This isn't going to be about deep into modeling. This is rather going to be about the challenges that we are facing with modeling. Okay, and it's a bit of a call to arms, maybe. also because I know that this is both industry and academia. So we're an industry in flux. We need help. So even if maybe the footprint of the automotive industry is not that large in the UK, but it needs help. So the work that you do can also have a very good impact on us and be very useful. So what I'm going to talk, so the way I've divided this a little bit is I'm going to talk a little bit about some global drivers for change. I'm going to talk a little bit about some technology trends, so you also see where the technology is going. I'm going to talk a little bit about the impact on how we do engineering. I'm going to give you a very short hint. I'm not going to spend too much time on that on our software-defined vehicle offering, okay, where we have a good strategic partnership going on. Then I'm actually going to get to the modeling part and look a little bit about what we're doing there. Okay, just a teaser, and then I'm available the rest of the day and happy to talk to anyone basically about concrete things, and a little bit of a summary basically at the end. I will try to build in pauses at the end, just at the end of each of these sections, just to allow for questions, okay? Okay, right, so I'm not gonna speak too much about this, depending on which guru you follow on LinkedIn. Okay, you have heard of case or space. Sometimes they add personalized or personalizable to these things. Okay, and depending on which have a different number there, 20, 30, 28, 35, whatever. But everybody seems to agree essentially that sometime within the next 10 to 15 years, we're going to have a kind of a standardized platform. A lot of the underlying architecture and basic technologies that provide connectivity, standardization of interface, that's happening now. It's actually even happening not only whether we like it or not. Yeah, a lot of people are. We're an industry that for many years thrived on exclusivity through obscurity. So there isn't actually a BMW specific connector. There's nothing specific about it except that it is BMW by physical form. Okay, the control unit hanging behind it is a standard control unit that basically is provided by us or by our fellows at Bosch or any of the others, basically tier ones. Yeah. And this simply doesn't work anymore. Level of customization is simply not financially feasible for us or for the manufacturers, and they don't care. They like to use euphemisms. They say non-differentiating components or non-differentiating software. That's a nice way to say I don't want to pay for it. Okay, so that's also a driver there. We're also seeing a bit of a difference basically in what used to happen. So for Continental, the value chain kind of it's kind of ended here basically with the manufacturing of the vehicle. So deliver our components, the vehicle is built up, okay, and that's kind of it. That's where our value chain stops. And that's not going to be the case anymore, and already is not the case. So we're looking at, due to the complexity, due to regulation, and due to a lot of other drivers, seeing basically that there is actually value creation beyond the SOP, start of production. Okay, and those are things that we will need to be able to do anyway, whether we like it or not. Whether we have an actual value stake in it is irrelevant, because recent regulations like the UNECE R155 and R156, for example, would require us by law, okay, to be able to patch security vulnerabilities. So I need to be able to reach into the vehicle, okay, and patch these things anyway. So if I'm going to have to do that, it kind of makes sense for us to try to also see if we can monetize that as well. This also fits, by the way, a little bit with these. So it kind of, you can make it become synergetic and try to see the positive in it, okay, because of the shorter expectations towards life cycles and towards the development and deployment. That we are also suddenly embracing that I don't have to have everything and every single end functionality built into the vehicle at the start of production. Yeah. So this means it's okay to say, well, this is the minimum go-to-market functionality. If push comes to shove, it can be the minimum legally required things to homologate the vehicle. Homologation is a term, essentially means to have it legally accepted by the country or authority, basically with that responsibility, yeah, that it conforms to the outgoing legal standards, yeah. So you can start at your bare minimum, and then you can add functionalities, yeah? And then you can simply say, well, actually, you know what? It's exactly like your phone. Continue to add functionalities as you go, and you will have a projected platform service life and so on. And this is already happening. So Tesla have been doing this very successfully. This is one of the things that they're doing well. Yeah? Okay. So again, looking from a value chain and very, very, it used to be the car. These things are relevant. We were speaking about stuff and maybe about philosophy being relevant also for STEM people. So, you know, cognitive models are important. They see only this. You will see this also affects, for example, the ontologies that we have for modeling. Vehicle as the center of the universe. Yeah, one vehicle. Yeah. So makes it very interesting when you start having to model fleet functionalities. Then suddenly your entire meta model has to be completely destroyed and rebuilt. Then everybody's screaming about their models no longer working. So. But yeah, the vehicle as one car. Then some basically will have maybe some added value services, some aftermarket stuff, some financing. So Continental actually has a service chain operating under different names in Europe. So we do that. Of course, we have a large aftermarket business with the tires and everything. And some of the car manufacturers actually, so there's a BMW bank and there's a Volkswagen bank. They do that. They saw there's some money to be made in there as well. And there's on purpose, a very small cloud because the services have been mostly laughable. Okay, some very, very weak tea. Or along the lines of, after 3 years, I switch off your seat heating functionality and then demand some money for turning it back on, which sounds more like a highwayman, basically, than so it's a bit of a racketeering thing going on there. Okay, but like I said, shows a little bit of a lack of imagination when it comes to this is traditional automotive business, yeah. And we're markets. Car is just one piece of a very big mobility pie. Here, it's all basically centered around cloud capabilities, and there are a lot of other industries, and there's a lot of other things happening here. I mean, payments. There's always a hidden player, insurance guys, also somewhere in the back, and very much affecting basically how business will happen. Okay, so that's just that section. I'm hoping there are no questions to that, but. This is the time. Speakers, good. Okay, so another thing that's also happening is that we're seeing a kind of a forced consolidation of architectures. So the way that architectures grew is essentially completely inorganic. If anybody has some affinity to investment banking, then know what. Basically, it means sometime in the 90s, standardized controller area network, the CAN, basically was introduced. Something similar to LAN, but just an ability to have a bus, so you don't longer have point-to-point connections. Somebody basically went gaga, said, oh, I can add as many control units as I want, computing nodes as I want. And that was, for 25 years, the business model. So the age that, they like to call it the age of ECUs and buses. I like to call it golden age for Continental and every tier 1 supplier out there. Where we basically said, you want a new functionality, you get a new control unit, and we used to sell these control units by the kilogram. Okay, so that was the business model. It's hardware with incidental software on it. Really, we used to sell them just by the piece. Okay, and this led to a massive explosion, basically, of the number of control units and the growth of accidental complexity. Yeah, everyone is just focused on getting their own little bits to work. Okay, and that's it. And that led us basically to a place where you might laugh, but one of the primary drivers for consolidation is packaging. There is no space anymore for boxes. Yeah. And just to give you a little bit of an idea where this is going, so the Volkswagen Passat, just a mid-sized vehicle. The one before the introduction of the CAN bus had 2 control units. Now, for the injection, and sometimes you had something for the ABS in the very high model. The first one after the introduction of the CAN model 10, next generation had 70 something. Current generation has about 100. The comparable S class has about 100 more, 200 little controllers. So there's simply no space anymore. And of course, again, they can't get them to work together anymore, like cats in a bag. So domain centralization is an intermediate step where they basically say, oh, look, all of these things are about the powertrain. All of these things are about what's happening in the interior of the vehicle or in the infotainment, basically. All of these things are about advanced driver assistance systems. So there's kind of a domain and functional cohesion happening there. So that's driving that consolidation. And we're also looking at moving away from these domain boxes and a little bit. I think this is currently primarily where we are. Some people a little bit more ahead and some people a bit behind. Okay, but the trend towards the next 5 years, so the architectures that we're discussing today, basically about cross-domain, starting the domain fusion primarily. So you look for synergies basically between, for example, ADAS and infotainment, both need hardware acceleration. Okay, so there is a little bit of a sense for them to be together in one box. The one actually needs more full accelerators and less graphic accelerators. The other one the other way around, so there's also a nice synergetic effect there. Okay. I'm gonna skip over these ones. So basically they're just the things that we want to do and hope to do. So managing the complexity and enabling plug and play and all the rest of that stuff. One of the important things to understand also is that, I think I speak about this, is that what also happened with these kinds of functionalities is that you had local each function responsible is driving their own local operation. If you look at an electric vehicle today, the biggest problems are global optimization. It's one actually primary thing, energy, and energy also goes into thermal management, and it's all one balance. I heat up the batteries, do I cool the batteries, do I preserve that optimal operating condition? Then how about the cabin itself? Okay, where am I spending my energy and so on and so forth? There's a lot that can be done with it. So basically what we hope and what we are working on today is basically, and already offering to some customers, is to have a zonalized basically architecture where you kind of abstract away. You don't see, there are still dozens of very, very small controllers, which we are now, was a trend for a while to build smart things. Okay, so you have a camera and you have basically the basics and the intelligence all into one housing. And we're actually starting to move away from that now. Consolidate the intelligence into one box. It allows you a lot more flexibility also with updates and new functionalities and upgrades and things like that. So we're trying to hide that. Essentially, this is abstracted away behind these little dots here. And you have these zonal devices which have also a geometric nature. Okay, also about using wiring harness. Again, you will laugh, we have banal problems, but copper is expensive. Okay, so expensive to build wiring harness. They're also heavy, that's also a problem. Yeah? They're also difficult to manufacture. Yeah. So if there's a lot of strange things happening at the moment. Strange in the sense also of how crossover is happening from one type of industry to the other. One type of application that was always isolated and never had anything to do. But Tesla has been applying for patents, or has been granted some patents in the past year, okay, where they are looking at replacing the central wiring harness in the vehicle bus bar. Anybody who studied electrical engineering knows bus bars as risers in buildings. Okay, this is how you use them. So in a large building, you basically build a solid chunk of metal going all the way up the building in a shaft, in an isolated shaft. and that's basically where you take off basically your floor level basically electricity from. But that's a good thing because it's you don't really want to have cables, a bunch of cables going 30 stories up, so it's dirty cables. You also don't want, with the cables, you get a lot of structural stability issues the longer the cables become. So Tesla is doing that inside the car, and it's more expensive. So this is also one of those things. All of these components previously, they used to be driven by individual cost and down to the cent and the penny. But now they say, no, yeah, the bus bar is more expensive, but by putting the bus bar in, it now becomes a structural element, so I can remove other structural elements. So I make the bar basically, it's weight neutral. So at face value, if I only look at adding weight, it's more expensive, but no, it isn't. I'm replacing it with other things. Important is laying down cables is manufacturing intensive. Actually usually involves people. So by introducing the bus bar, they think they can push out just about 15 minutes actual labor work per vehicle. That's a lot of cars on the manufacturing line. So they're actually getting it out from an even higher level of globalization, which is not about the building and the operation of one vehicle, but it's about their manufacturing process. So again, I'm trying to give you a little bit of an impulses about where the game is going for us. So it's no longer about how do I model an individual system. It's about how do I model the individual system throughout its life cycles, also including things that are usually forgotten, like the transition to manufacturing, or the transition from manufacturing to operation. Okay. Like I said, so we're seeing a little bit of a consolidation also here. This is domain orientation, and this is where we, I've already gone actually with a lot of things. So we have both horizontal integration and vertical integration. Just to give you some numbers also, so really we're seeing something like 10 to 15 times jump in all kinds of numbers that we saw before. I always like this number, particularly with the footage. I remember a long time ago when I was young and dinosaurs roamed the earth. I was like, basically, I really was destroyed by some big project manager because my control unit was consuming 4.6 instead of 4. So this was a problem. So much energy and so on and so forth. And now I find myself sitting in meetings where people say, yeah, 1 kilowatt, yeah, liquid cooling, no problem. What? Yeah, that's happening now. So, right. Okay, so we've actually already, so this is not theoretical stuff. We've also introduced, actually we've already introduced the start of production in 2019. So the first, please excuse the, we like hyperbole, okay? So we call it high performance computing. It has nothing to do with high performance computing, a STEM term. Okay? It's just a really big ECU for us. So, you know, we're of magnitude larger. So we needed to use a big term. Fortunately, we used the word high performance. So I don't know. We need to think the next order of magnitude will ultra performance, and soon we'll run out of words. I think in 5 generations, you will hear bombastic performance. Yes. Okay. The word holistic also means nothing for us anymore. So we've basically completely pillaged that one. Right. But you see here, so the it has a link to 68 other small control units. So it's also functioning a little bit as a gateway. We've talking about 30,000 protocol messages that are being sent. 19 companies working on the software for a single ECU. None of this is normal. It also explains why we had a lot of challenges with it. But none of this is basically normal for us as an industry. 70,000 stakeholder requirements, 60,000 of which you could probably ignore, but you can't. Okay, these are things that vehicle manufacturers like to call them other binding documents. Yeah. And the other binding documents will include things like, well, at Volkswagen or at BMW or whatever, we like to use the color green when we code. Okay, things like that. Flashing should of the devices and devices should occur only to Mozart music, okay, and other extremely engineering relevant things. I make a joke, but some of these things, some of these documents, of course, it is unreasonable. It's a part of trying to lay off the work on somebody else. Okay, so they have a lot of complexity, so they shove the complexity on somebody else. But you see also what everyone is dealing with here. And it is, of course, quite unreasonable to expect anybody to really read any of these or anything like that. I've actually had this state where I was a lead architect for a very big box, and I joined the company and hence the project 6 months after it started. Discovered very quickly that a couple of things that were problematic, and I was wondering who on earth agreed to this. Went back through the initial agreement documents, and you would see there was a requirement that all vehicles from this manufacturer needed to be able to go through a complete over-the-air update cycle, okay, and be done in 10 minutes. So you can't expect the customer to basically forego their vehicle in 10 minutes. The 10-minute cycle actually included a 99.9% completion then failure. So it was actually the time that you had for 2 complete flash cycles. So you needed to be done in 5 minutes. And then I take a look at our device, and it's essentially a bunch of chips that are hidden behind each other. And there is a bus between them. The bus has a theoretical maximum bandwidth, which even if I saturated with no protection protocols whatsoever, I would still not be able to transfer the amount of data that I needed to transfer in 5 minutes. So it's physically impossible. And I thought, this is bad. How did this happen? How did nobody notice this? I scroll back through the actual agreement requirement documents, and there is an actual, somewhere down there, somebody actually took the time and did the math. There is an attached Excel file that shows why it is physically impossible. And it says rejected. And it actually says between big air quotes in all caps, physically impossible. Yeah. And then somebody, when the project needed to be accepted or rejected, because there were 3,500 of these requirements, basically just flip the entire document to accepted, and basically we deal with the problem later. So again, finding out what is relevant is also a big issue for us. Okay, I'm going to speed up a little bit. So the impact on engineering, I think I've kind of teasered some of this a little bit. We have this software-defined vehicle is now the next buzzword, basically, that we're working on. Unfortunately, like a lot of other things, people think the software-defined vehicle is primarily about software. It isn't. Okay, just like software-defined radio and software-defined networking before that were not primarily driven by software. Okay, they were driven by systems engineers with a very hardcore hardware background. Okay, and the same thing is happening here. It's how can I basically abstract my system the right way, okay, change the interfaces to my hardware the right way to enable changes later in things that I want in software. So of course there's a lot of software expertise involved, okay, but this is a bit of a problem, and it is a problem and a trend currently in the industry. So also you will see that there is a bit of a discord and a disconnect between our old classical engineering guys and between the new younger generation, maybe software engineering prowess. I say software engineering, but I think it's also a lot of just programming, because software engineering is a discipline, and actual software engineers, I have no problem with them. People who just think writing a couple of lines of code, see, look, it works on Mondays when the sun is shining. And that's why I'm going to test it out now on public roads with human beings. So that's not software engineering. Okay, and that's a little bit also the discord that we're having here. Okay, but these are the things that basically we hope to achieve, and we are actually achieving also, including this code to road within 1 day, which always gives my braking safety colleagues basically an allergic reaction, which is understandable. No, I don't mean we will develop a new braking function in one day. But if you have a security patch, security vulnerability that is discovered, you will need to patch that within one. So that's definitely something that we're considering. And not considering, we're doing that already today. And we also hear this a lot, so I like to have a counter slide to that. The mobile phone on wheels. Sure. Well, here's the difference. The mobile phone, basically, I mean, you see the numbers, but the most important part is, you know, when your mobile phone doesn't work, annoyed. Hopefully nobody dies. Unless you have a tendency of throwing it very accurately at people's heads. So it's a different thing. But faulty software in a car is fatal. Yeah. So we can't really afford to, we really are doing our best to get the best ideas and really refresh the blood. Okay. But there is a limit to how much lightheartedness, let's say, we can afford when it comes to these things. Okay. I'm going to use this analogy. I like it. This book by Simon Wardley, which I can also recommend. Uses the analogy basically of the Wild West, okay, to talk a little bit about how products also evolve. So at one point you have this genesis basically phase where it's all about survival, you know, first one arriving on the tree. Okay, and then you have a small settlement, maybe a little bit. You have handicraft, so you have the guy who knows how to tan leather well, and then kind of give your leather to him to tan, and so on. And then at one point you basically get more towns, yeah, that have now actual products. So you have an actual saloon, and you have an actual clothing store, and so on and so forth. And all of this is basically grows very organically. And then you have, at one point, you have these communities, yeah, that are actually planned towns, yeah, the town planners, where you have grids and spoken wheel and so on and so forth. And those are different. And your products kind of also is, and so I want to talk about these different kinds of product engineers, pioneers, settlers, and town planners. And to be very frank, just to I don't like to build up too much trauma. A lot of work in automotive has a strange duality of being kind of in the pioneers but wanting to be in the town planners area. Okay, so due to all of the car manufacturers also wanting to be unique, having that Audi feeling, okay, or whatever. This also means that they always request highly customized one-offs. Couple that with other engineering, management, and planning tendencies in the industry, and what we primarily reuse is people, not engineering artifacts. So, although Stefan is an expert on this topic because he worked on the last project successfully for the last customer, so I'll take Stefan to any engineering artifacts and staff him on the next project. He'll bring a couple of the guys that he worked with. This is the recipe for success. And there's a limit to that because also with the explosion of the complexity of the technical item itself of the system, there's a limit to how much Stefan himself basically can also scale internally. Yeah? So the software in the system, what we had is in the past 20 years, primarily too little systems engineering. Okay, so you have some systems guys trying to understand the product. I have some software people who actually have code and have already defined the architecture bottoms up. Okay, and you talk to them and they say, I have no time for paperwork, because that's what systems engineering is basically viewed. So for trivial systems, mathematically speaking, the human brain can still scale up to complexity. So if you have an experienced enough guy, they probably will get it right. And whatever they blundered on, okay, will probably be correctable later under the paradigm, one box, one function, my own little realm basically, in which I have control of everything, also the interfaces. then I can basically correct. Now, once I move to one unified box and shared resources and so on, it doesn't really scale or fly. And we also saw some people with too much systems engineering. So you have some systems guys with some nice, very, very detailed architecture models using SysML to or down to the silicon and so on. Wonderful stuff. And then the software guys had actual code and waving sunset. You know, and nice disconnect there as well. So wondering about what you're spending your money on. Part of the gap is also, by the way, a problem with standardization. So for many years, the word architecting meant different things if you spoke to people from software or systems background. Okay. UML and SysML standards, kind of similar, but not really. Okay, so that's also a bit of a problem. A use case in UML is not a use case in SysML. We're talking about people that only know UML, then it takes about 20 minutes until you discover you're talking about different usually. But this is also, the gap has been actually closed. So 2015, the ISO 158 was updated with a lot of software guys' involvement. That's the international standard for systems engineering processes. And then the ensuing 12207 update in 2017 was then completely aligned. It even says in the foreword, systems engineering is completely basically ISO 15288. Okay, and hence everything looks the same up until you get to the component where then you essentially have domain or discipline engineering. Okay, and then they both point to each other basically across the line. So I've noticed that I have less problem communicating with younger engineers, okay, than with the people who are in charge, okay, who even if they have a good engineering background, will have grown up in an era that basically uses different terminology and has a different understanding as well about what has to be done. Okay, we can kind of skip through this a little bit, but basically this is usually, like I said, the area where we were. So we do the customer projects and then you rinse and repeat. Okay, and then currently what we need to do is to have platforms and programs, and that's also a little bit where we struggle. So how do you basically do that well? It's flexibility. Okay, and this isn't just processes or technology. So I stole this from a very good book called Cloud Native Transformation. It's offered by a couple of really clever guys called at the company Solutions. They really know what they're talking about. The book of patterns about digitally transforming companies. Okay, so they both have like also technical patterns, yeah, but they also have things about basically pitfalls about dealing with people. So that's actually quite nice. There's a raging debate currently about whether design patterns are good or bad for software engineering. I don't know about the early ones in the Gang of Four and so on. I think those were useful in the object-oriented programming paradigm. But design pattern, actually, if you follow the conference, has actually moved on from that. And now they talk about design pattern 3.0, 4.0, and so on. And they're talking also about how it applies to human interactions and so on and so forth. So I think that part is still kind of relevant. Okay, so I think we've gone through this a little bit, so I can fast here. So we basically had these one-to-one trivial mathematical relationship between basically what the customer expects, what we would build in, and then what the physical manifestation of what I would deliver. Okay. And now we basically have this very, very nice picture, okay, where what you actually have is, so there's like standard services, and then there are communal parts, okay, and then there are customized parts. So how many times do you want to develop a trajectory planner? If I have 17 ADAS functions because I need 17 ADAS functions to fulfill Euro NCAP ratings, okay, that's a crash safety, basically, expectations at the level, yeah. Does that mean I have 17 trajectory planners in the box? I hope not. So that means you'll end up more actually in a picture like this, and this is actually already what we're building today. Then if I start also building these domain and centralized higher performance computing, it's actually going to be a picture where I can no longer say this exactly is my system, but it's rather going to be this blob here with some parts in the clouds and some parts even in maybe places where Continental even is not delivering this thing. Or maybe we just need to either deliver a piece of software, or some parts of the chain of effect are not even in my control at all. Maybe I don't have nothing to do with steering and braking, but I need to interface to them basically to perform some emergency braking function or something. So again, even for the functionality, okay, we're talking about systems competence, okay, and this is a picture from Boston Consulting, or one of the consulting companies. So they talk a little bit also about how everything essentially below this layer, the application layer at the top, okay, is what people like to refer to now as non-differentiating software and hardware, aka I don't want to pay for this. So see that standardized services, be it inside the vehicle or outside, they want ALIS, hardware abstraction layer, so they want to decouple as much as possible. Okay, and again at the end, basically this electrification with domain-based component, and they also don't want to see any of this. Yeah. So our own offering, it's called KEDGE. Please don't shoot me. I didn't come up until automotive edge framework. Comes from the idea essentially that we want to flip the narrative. The vehicle is not the center of the universe. Maybe cloud is the center of an ecosystem. Okay, and in the cloud, those are just another edge device. Yeah, and that's the way that we need to look at it. Okay, because we also had internal narratives about we are automotive. We tell the cloud guys what to do. So that was a funny conversation to have. So we're actually also happy to report that we are basically considered by the Gartner Hype report, which is exactly what it sounds as hype. So please don't. At least if it comes to hype, we're being hyped basically as one of the top companies in software development. And what we have, if this picture looks familiar to the BCG one, it's because everybody is kind of coalescing to the same concepts. Ours is actually earlier; it's from 2020. So they're copying us, not the other way. But this is exactly what we have. So we basically have one standardized, basically DevOps workbench out for the entire company. With collaboration space, cloud-based, and so on. We're standardizing this high-performance computer APIs. Okay, the vehicle API is being standardized. We also build middleware with our Electrobit company, which is basically the own subsidiary of Conti. And we have a partnership with AWS, but we also build on-prem, basically, compute and so on. So it's all there. Okay. And this is one of the first things also where we really prioritized platform engineering at the beginning. So, for example, the simulation and validation services, it started in 2020. We had a customer who came in. This was a real paradigm shift for Conti. It's standard business for everyone else, so please don't laugh. Okay, but it was a paradigm shift for us. So it wasn't the person who buys my car wants to have this functionality. Rather, it was my engineers need to be able to observe field data, collect that, pump petabytes of information into simulation loops in the cloud, and use that to see if they can't improve of safety critical functionalities. And then use that to change the algorithms, basically create software, pump that out basically to the vehicle. And that's standard for mobile phone, maybe, but definitely not standard basically for auto scale. And we did that. So the numbers are basically for us were shocking. Yeah. So the entire project, we did a hackathon in the beginning, had productive software after a week. Usually the first hello world things you see in an automotive project are 6 months later. On a 2 to 3 year basically project. Then we were delivering software basically weekly. Within 3 months, we were delivering software every day. In 4 months, initial basic functionality was finished. It was closed in 6 months. This was unheard of. The really unheard of part was everything we built was now a standard piece of our offer. So it's there. I don't need to do simulation and validation service infrastructure anymore. There. Because we use the standardized API approach, because we basically went API first about it, and so on. Okay. So skip the slides. I mean, basically, these are the things that you can do. So we have a lot of virtualization in the cloud where you can validate architectures before you build them. We can run all of these functions. You can drive a lot of simulation data, share the same target hardware. So we also have a hardware farm, basically things that are also, again, standard for mobile phone development. Okay, but we are basically doing this now a little bit. It's new to us, so we're excited about it. Okay, this is the setup that I was talking about. So basically, we had really, these are the actual cars using. So basically, you would collect basically a lot of information in the car. You can do silent testing, analyze the data. You basically put it in this data factory. Then you do the algorithm optimization and back, and they call this infinity simulation loop. So this is all basically, these are actual pictures from. We're having now the same thing at a much larger scale. It's public information. So we have a partnership with one of the serious basically players in the autonomous vehicle market. They're one of the most serious ones. They're starting with an actual use case that makes sense, which is long-haul trucking. Okay, so we're also their partner there on industrialization and aspects. We're also delivering components, and back path also is being delivered by Continental, about engineering diversity in the design. So that's also something very exciting. And of course, they rely on a lot of simulation and driving. So I'm going to skip these. You will get the slides, and please have this. An important thing to also understand, can't do everything exclusively anymore. So a lot of what is happening in this ecosystem is also about standardization and work. So there are a lot of interesting initiatives happening now. There's an Eclipse-based software-defined vehicle, basically a consortium that kind of covers more or less everything, and people are contributing a lot. For Conti, it was also new. Some bosses are still get it. Why are we now open sourcing some of our things? Okay, so this is also a very new world for us. So please bear with us if you reach out to somebody at Conti, and remember to have a varied experience. But we're trying to get there. Right, the interesting part finally. Sorry about that. Okay, so this I should have made a disclaimer. Somebody told me that I should always give an epilepsy warning about most of the slides I generate, and to at least induce nosebleed. So sorry about that. But basically, this is the way that typically vehicle manufacturing basically is product. So you start sometime 5-6 years in advance, discussing with one premium German manufacturer now about 2020. That's not as stupid as it sounds. 2029 is when it will appear on the market, which means basically start actual development work. That. Okay, so the 2029 model essentially means everything is done by the end of 8. Okay, so 28, 27, 26. Okay, so those are 3 years basically maybe of actual development work, which means we have only the next 2 years to finalize everything. Yeah. But still, 5 years is kind of a number. The Chinese guys are a lot faster now. They look at 2 years, but they also accept, I don't want you to develop a hardware for me. I will take whatever's available. Yeah. Because of the car needs to have everything by the time it hits the market. It kind of also makes you reach a little bit. Yeah, the hardware can do. So kind of try to come up with this concept, and there's a lot of guesswork and a lot of expert-based analysis going there. Okay, most of it is not formalized in any way. So it's really just a bunch of people scratching their heads and shouting at each other. There's a lot of shouting involved in these things. And then at one point you think maybe I've minimized the risk a little bit by shouting. And then you go to hardware selection. The hardware selection basically happens on which of the marketing slides silicon providers do I believe most. Okay. So, because all of them are going to promise me magical chips that can have petaflops of performance and L pattern boldness and a lot of other wonderful things, basically, in 2 years, and that 2-year target is always moving up, actually, when it comes to the pattern boldness part. And then at one point, then you have the samples available. Sample, A sample, B sample, etc. And once the samples become available, and depending on how stable they are, software application can actually, so the actual function development can start. That's the timeline. And then here we're talking about the last 2 to 3 years. It's kind of roughly, or here you can start and anticipate what the hardware will look like and write some basic drivers and so on. And then you have a lot of function refinement and adjustments and so on. And this leads basically to this kind of curve when you're talking about risk and maturity. So very up close to the SOP, basically, still a large amount of limit. And what we basically are doing now, we're trying to leverage data models and the increasing availability of cheap cloud compute, okay? Huge amounts of data which were unimaginable 10 years ago is daily business now. And we say, well, let's combine some things. Let's try to do an early vehicle architecture concept validation. So let's try to see if we can do some formalization there. Actually take some of that risk out. And then we can immediately start with virtualized ECUs. And has 2 benefits. First of all, you can immediately see if these virtualized ECUs basically fit in the architecture, so you have a nice feedback loop there. Okay, but you can also use the virtualized ECU models at very good parity to actually immediately start your software application development. And again, this isn't rocket science. This is all kind of available for a lot of things now, not at this scale and not for this kind of safety critical application. So these are, let's say, the new add-ons basically to the complexity. But by doing this, also accepting that not everything has to be, or no, it's not everything, that sounds negative. Let's do it positively. We'll need to continuously add things and update and upgrade you. Imagine smartphones. Imagine if I'd come to you and said, full device, right? Do you want the new weather app? You have to buy the next iPhone. It is as stupid as it sounds. And if Steve Jobs had done that, iPhone would have never worked. But we've had 100 years plus of doing exactly that to our consumers. Yeah, you want the new green color on your touchscreen or whatever, you need to buy the next BMW. Yeah. And that simply is not acceptable anymore. Also, again, I'm going back to the sustainability angle. Part of it is not about recycling everything. What's the point of recycling everything if you need to throw it out every 6 months? Part of it is extending platform service life, and that's really one thing where I commend Tesla. If you've bought your Tesla Model S after April 2016, today you are able to get the latest and greatest functionalities. They continue to be able to basically deploy that software to you in this version. Okay, so that's really good. You don't feel the need to basically go to the next one to get the next weather app. Okay, so what we really are aiming for, and what we've started to already actually achieve, is a shift left basically towards the risk. So I achieve lower risk basically at much earlier phases. I'm also getting a maturity shift up. So at these earlier phases, I'm at a much higher maturity. And in general, I've started to be short in our development cycles. To understand a little bit about the modeling stuff that I want to pitch, maybe just a quick introduction into how we are basically looking at our world, Continental. So we have an ontology basically that does both separation of concerns and divide and conquer. So the separation of concerns happens via system views. This is new, I hope. Yeah, so ISO 420 and 20 basically, I think Parnas spoke about this in 79, so it really is quite old. So we do this. So essentially, if you're not familiar with views, it's essentially think about building a house, okay, and you have multiple stakeholders, and you have plumbing people and your electricians and your interior designers, and maybe it's not a good idea to have all of those things on one picture because it will be difficult to understand. So you want to separate those concerns. You have plumbing, basically, diagrams and schematics, and you have these wiring schematics and so on. But at the same time, there might be an engineering reason why these things could be related to each other. For example, you don't want these people to grill each other. Okay. You might even want to understand where the structuring basically diagrams, what are load-bearing walls. Okay, so your interior designer doesn't decide to hang his head from a paper-thin wall, something like that. Yeah, so you're into that kind of thing. And that's basically what we do here. So we basically try to separate this, and this is, by the way, also a little bit kind of newish to Continental. So I think to introduce this about 6 or 7 years ago, primarily also for the automotive industry. Problem space was so well understood that it was always skipped in analyses. This is a trend that engineers do. 15 years ago, I met a very senior engineer, Rolls-Royce, the guys who built the turbines, nothing. And he used the term, which I like very much. He said solutioneering. Okay, which is what happens when you ask an engineer to describe the thing that he is building. He'll tell you what he is doing and how he is building it, what it is or what it does. Okay, and that's a little bit of a problem because, again, if it's a trivial system, then that's not really a problem, and you're fine with 3 boxes kind of collapsing into each other. But if it isn't, and if you have cross dependencies to other systems, okay, then you need a lot of explicit, basically, specification in order to make sure that your job well and also able to do that. Okay, so this is basically one picture. The other is basically we have some abstraction layers and hierarchy levels. Okay, and so you see this the level of the vehicle. Okay, we actually introduced. So I'm very proud of this. The used to be non-existent. We used to have numbers. So the vehicle level used to be L0. Shows you basically L0, 1, 2, 3 downwards. Okay, but that's it. And I joined Conti as lead architect for driving. We said, well, have expectations and requirements towards structure or other vehicles like that. So we started collecting a lot of L-1 requirements, as ridiculous as it sounds. And then people were like, what are you doing? This makes no sense. I can't, the system and the process and so on. What the hell are we going to do? -1. The actual process description tool refuses negative values. And it makes no sense. And I actually have a handful of L-2 requirements. Yeah, because this is a socio-technical ecosystem, a little bit, the LE, but we're also talking about an ethics machine, for example. Yeah, who decides the kids versus the grandma question? Outed quite often in the debate about the ethics of AI. Yeah. If it's a human driving and they're put in the position where they have to make a very bad decision, then it's a tragedy no matter what happens. But it's also considered, one-off tragedy, and that's fine. And nobody knows what they're going to do in that case. And it's fine. It's kind of, you accept randomness even if it is not true randomness in that decision. True randomness hasn't achieved really. computing, so I would have to build in based response, decide a priori whether the grandma or the children basically are valuable. And I don't want to make that decision, so I basically just pointed to a higher level requirement. That it comes from there. Those are the guys that are going to decide whenever they do. But I did have those. So again, it's banal things you want to model, but understand that nobody can actually take your resulting requirements. They are unable to take them because they don't have a container to take them in. Yeah. Okay. Right. So we have all of these things. Some of the work, for example, that we've been doing in the past year, the L1 point, so unaccepted in the beginning, has now become a standard thing at Conti. So standard, whatnot, unfortunately, that I make the joke that E now stands for everything else. Okay, so everything outside the vehicle has become a dumping ground, basically. So we needed to provide some there as well. So we've relied on, and again, actually part of what triggered the discussion was people would, some colleagues would come to me and say, we took our ADAS camera, we put it in an intelligent intersection. Is it now an L2 or an L1 requirement? What? I don't understand the question. Oh, hang on. You're trying to force our ontology down the road of down the throats of other people. I see. They did the same thing with the cloud as well. So they were asking me about whether when they shove a functionality into the cloud, is it now an L3 or an L4? And I said, again, I don't understand your question. So what actually is happening is we have used established ontologies because there are subject matter experts in these other industries. I at least acknowledge that fact. Okay, so what we're trying to do is really use some ontological interfaces, basically within necessary semantics being expressed at the interface. Okay, so that I have a structure. So road transportation ecosystem is one. The digital infrastructure telecom ecosystem is another one. These are systems of systems, basically, and multiple of them actually at that. And cloud-enabled things is also its own ecosystem. Yeah. And we should stop trying to tell them what the architecture should look like, and we should simply learn to express our expectations at the interface. Again, also not usual for somebody who is used to having their own box, which is also their own fiefdom, basically, and they do whatever they want inside there. So learning to work against standardized interface is a thing. So this is also something that's now being included and rolled out into the standard data model, basically, and for content. And helping us do some things. And even you will see the cat is here for an actual reason. So we try to test it out, see if the model actually holds also against just standard non-automotive examples. So if instead of a dispatcher, a driver, or a passenger, or whatever, what if I had a cat and it wanted an automated feeding station? Okay, would this model still hold? So yes, it would be a direct system interface that it calls at, right? And then basically through that interface, basically to the digital infrastructure, into the cloud, through the cloud, back to the mobile device to me. Okay, so modeling still holds. Okay, so, and again, I don't need anything about how these things look like internally. I just need to understand where do I assign requirements. Those guys take it from. Okay, so if I now map a little bit, basically this layers and these views onto each other, and we see a lot of modeling, and primarily because Conti's business has been a little bit essentially at the box and maybe the systems made of boxes, so somewhere basically towards the middle, and because previously work used to start in the solution space, so it really used to be that modeling was kind of focused in this box here. Yeah. This part of. See, we're trying to expand basically, but we say this is the blue boundary is basically where you can model, should model, and a lot of activity is here, and even this year. So I'm also the chair for internal systems engineering, which happens once a year. And I actually accepted one. Normally, I would have rejected it just from desk. But I accepted a submission by one guy who showed us how he was modeling silicon level flip-flop, basically, SysML. And my only question was, why would you do that? Yeah, I mean, given the availability of DSLs, basically, that are much better adapted to that, given the fact that this is something that you get from a silicon provider usually, what would be the purpose? And he took 30 seconds to provide a non-answer, which I can cheekily boil down to the same answer as, why does a dog lick its private parts? Because it can. And this really reminded me of a conversation I had 20 years ago with a guy who was an expert at MATLAB Simulink and used to do his taxes in Simulink. So it is one of those things, okay? Just because you can does not mean you should, okay? So excuse my profanity, but this is a trigger definitely for that. But what we are actually experiencing is that this part is a part where essentially you're already caught up. Silicon providers are now happy, and it's part of the expected delivery by the increasing parity model. Then you also have the actual software there, because we're trying now to no longer dump and rewrite software every single time from scratch. So I have the hardware model, I have the actual software. What am I modeling the system exactly for at this level of detail? I'm talking about a software unit. Yeah. So I'm pleading for a shift, and this is also what I'm pushing at Continental, towards this upper left quadrant. Okay. Multiple reasons. Primarily, this is the area essentially where domain discovery happens. Yeah, this is the area where we're now crossing into other ecosystems, where we need to learn to cooperate. Cloud guys are not automotive experts. We are not cloud experts, okay, and so on. So also, from a return on investment perspective, time model interactions and customer expectations here, they have long-term stability. These artifacts are stable long-term. People want to be able to be driven from point A to point B. Yeah. Even going down to a level of detail, automated lane change. That's also kind of stable long-term. So if I describe that feature interaction at that level, that's okay. If I start describing gates and APIs and I don't know what, that can change. Yeah, look at Swagger. Yeah. API itself, the framework is changing every couple of months. Just keep updating. So the question really is, what am I doing basically with the model? What do I get from that? So these are also the largest gaps in the systems understanding, and that's really where I think that we see a lot of things. But it's not only about this. Please understand also there is a missing view here, which is about the life cycle. So again, we think a lot about the concept in the design phase because that's what's cool and sexy. Yeah, I get it. Okay, but there's also, at the end of the day, you want to provide usefulness and value to beings. So this only happens if you can transition successfully to manufacturing, if you transition successfully from manufacturing through commissioning basically to an operation. You can maintain the operation long term, it's a good thing. If you also think about autonomous systems, for example, then you get a lot of additional requirements about the deployment of systems. Some of these are actually now being regulated. So for a time it was the wild, wild west and everybody did what they want. This is a problem, by the way, with trying to abuse regulatory absence. At one point, regulators get pissed off. This has happened now. So the NHTSA, for example, in the US has issued a general standing order in 2022 that said, if you have any kind of incident, an automated vehicle, and they also include basically these assistance systems, so not autonomous, but actually automated, you need to report it within 24 hours. So suddenly everybody was scrambling. What does that mean? How do I do that? I have the privilege of working with intelligent people. So in 2018, as a response to some clear incidents we were having with field we started thinking about safety management system. It's not a technical thing, it's an organizational thing. It's a management system. And we introduced that at Conti as a Sunday afternoon activity. Nobody was interested. We just did it because we thought it's a good idea. I was very lucky. I had a couple of guys, very experienced guys as colleagues, basically also had a very deep background, long years in aerospace. Such things are normal. So we look basically across the industry. I'm very proud to stress that I'm a proud plagiarizer of these things. So systems engineering management and template is shamelessly stolen from a systems engineering handbook. Okay, because why reinvent these things? Are there other industries have gone through these pains before? So this, if remembering basically what we're doing, actually what we are. So we have actually purpose-built models, high levels of abstraction, idealization, that we use with design space exploration. Yeah, we have a formal methods basically driven approach here, okay, and some nice DSE stuff. And this allows us basically to do multi-criteria optimization and constraint search basically at level. And then I basically come up with a nicer validation basically of my concepts. We don't cover everything. We cover things that are, again, automatable so that the guys doing the shouting can now focus their shouting on things that I can't do. This already takes a lot of the risk out of it. Then I use these currently manually translated, still getting to the point to automate the cycle, as an input for these virtual ECU builders, basically. So we have this one already kind of up and running. It works on Mondays when the sun shines. And we're working on this one. So this is our big thing for 2020, basically to get the entire virtual vehicle. So essentially it's a replication of the virtual ECU builder in multiple instances together. Okay. And this will basically provide that loop. But here I'm trying to, as much as possible, use actual software layers, okay, and come closer basically to the parity. So here I would be working with a bit more idealized basically ECU simulations, and at this level I would then be asking about IOs and the silicon basically effect. But that's basically what we are currently doing, and I'm going to get so this is a lot about mindset and organizational change. So I did my research stint, my time at was a nice transition from yet another meta model to yet another DSL or something like that. So everybody basically came up with their own grand unifying theory of everything, okay, that barely worked on Sundays shining. Okay, and rarely had anything to do with actual problems in this is one of those things. I'm supposed to be an MBSE champion. I hate words like champion and evangelist, and anybody who uses them in my vicinity gets shot. But one of the things I find myself most often doing is stopping people modeling. You can't answer the question, why are you doing this? And if the answer is definitely something along the lines of to please the process gods, or because I have to use this tool or anything like that, okay, then please stop modeling. Who is your stakeholder primarily? Who's going to take this artifact from you? The results coming out of it? You can't answer this question clearly. Please stop modeling. So there has to be a clear purpose. There also has to be a clear purpose about basically, again, what is the return on invest? So if I put 50 hours of modeling into this, is there a 50-hour, let's say at least, of engineering saving happening down the line? So again, please explore as much as you want in academia. Need that, yeah. But it would be nice, yeah, those of you not fundamental research. Okay, if you could really explore this a little bit. So I'm not talking about aspects of usability, that comes later. I also I've presided over the building of tools that are from geeks, for geeks, and definitely come with a nosebleed warning. Okay, but just consider that. The architecture and the emergence issue, so it's also a continuation of are agile now, so that's why we don't have project plans anymore. Debate, okay, so everything is now by software, so I don't need an architecture. That's a statement I heard from somebody. Okay, so that's again a false understanding. I think it's based back in the UML and old days of software, where architecture or architecting was actually the verb to describe doing design work. That I understand. If you have an API framework, then we don't really need to talk about design, but it means also that you have a stable product architecture framework. And then essentially everything that you build with a standard API would fit automatically. And the basically closing the loop. So I think there is still a place, definitely, for systems engineering, okay, in the grand scheme of things. But I do think that it needs to be in that upper left quadrant, okay, and to work on early system validation and also understanding, again, domain discovery really has been my grand takeaway the last 10 years. Talk to people. First of all, they wave you off. I'm an expert, I know everything. Okay, fair. But can you explain to me, like I'm a 5-year-old? So what happens first? I do this, and then I do that, and then I don't use dirty words like SysML or city tool, magic, whatever, something. Okay, but I did just actually drop down an activity diagram simply by asking questions about the sequence of things, basically discover, oh no, that's inconsistent. And I can't tell you the number of times this has happened. So the systems are becoming complex and beyond also our ability, unhealthy doses of ego, to also recognize our own limitations. Yeah. Okay, I think this last one is quite important. So these virtualized models also that you're building, they will help later on also for digital twins. Digital twins themselves are very important to maintain what I like to call continuous. Okay, yes, that's a term shamelessly plagiarized from aerospace. It's called continuous airworthiness there. Okay, so airplanes basically, once they land, they're grounded. Okay, they're not allowed to take off again unless you can prove a certain set of procedures that show that the airplane is safe. Some of these are long-term things, so that there's an actual maintenance plan, long-term, basically an observation and so on and so forth. And some of these are things that you would have to do immediately. So for airplanes, for example, the pilot has to do a walk. Okay, finally, last thing to make sure the engines haven't fallen off or anything. And then basically they're allowed for takeoff again. So the same thing basically would need to vehicles, and now just imagine it's not one airplane, okay, where you have a large infrastructure and a regulatory body behind it. Think about all these autonomous trucks driving everywhere, and we need to have those as well to maintain continuity. And these are not, none of these are basically high theoretical rocket science problems. Think about it this way: I release configuration. So for aircraft, it's type certification, right? Then it's this airplane with these exactly this way. And if you change the color of the seats, you need to have an analysis that says that the color of the seats is not relevant for the type. It sounds like a joke, but changing the color, change the material, which might change fire rate, and basically it might change the weight. So, and just imagine now this for your bought a shiny new BMW automated driving, and given what I've told you how the industry runs, hardware was selected several years in advance, trying to minimize risk and trust, which means at SOP it's already technically obsolete. Camera basically that driving. 2 years later, if you're me, I'm talking about demonstrator, so get a stone basically into which not only breaks your windshield but also the camera. Now here's the question: logistically speaking, am I as Continental supposed to maintain warehouses full of technically obsolete cameras so can rebuild basically or get back your automated driving system, am I supposed to keep these warehouses? Would it not be simpler to replace it with a newer camera, which is 5 times better and 5 times cheaper? How do I get the certification now back? So recertification in field. It's also a thing. Okay. So what we are working on and what we also really look for is basically this API first for systems, ontological modeling. I'm sending a lot of work being done JPL on that. OpenCaesar is a thing for anybody interested in L2 based activities. There's going to be a nice panel and a workshop on January 31st hosted at JPL in Pasadena. I'll be there. Okay, so thinking about modeling also as I don't know, I think I've seen the term before somewhere, model ops, yeah. But think of it really as not only about concept phase and so on, a development phase, so in operation and how that essentially now just a cycle, okay, that continues. Please, the framework for everything, if you want to do that, and if that's your PhD, that's fine, okay. But we really now are looking at model federation and interoperability basically as prime drivers forward. Exploring and guaranteeing dynamic configurations is the thing. We have a big problem with configuration management in general. Okay, so and it becomes worse. And by the way, this is again to the fact. I had a slide somewhere. It doesn't matter. And Samsung Galaxy had 2021 physical configurations. Okay, this has now been reduced. So the current S23 generation, because they dropped, for now at least, their Exynos, the Samsung own basically silicon. This has actually dropped to 15 configurations, and I'm including color variants in that. Hardware, just hardware, there are only 3. Okay, so that's a consideration. In a BMW 7 Series has 10 billion physical configurations. A couple of those zeros are ridiculous. You can they're related to the color of individual stitching on rare rhinoceros leather seats. Okay, but even if you remove 4 zeros, that's still a big number. Yeah, so the scale of the problem is actually a thing, and it's killing us. And again, use it as a term, minimum viable architectures. Okay, what is the amount of work that needs to be done? And I'm telling you, there is an amount done. Okay, we need control. Basically, be able to use 1+ things. They're getting heavier again because of the battery that can kill people. Right. I'm going to wrap up here. Thank you so much. Oh boy, I'm a little